For this lesson, we're going to be continuing to extend our study of vectors. We've recently looked at vectors in both R2 and R3. For this lesson, we're going to focus once again just on R2. And the main idea that I'm introducing here, I think most of what I do in this lesson will be fairly intuitive. There's one part that might be a little bit tricky, but the key part that I really want to have you focusing on and remembering and starting to make use of is the idea of the unit vectors. And in particular, it's the unit vectors for the x and y components. So those are traditionally named I with a vector above and j with a vector above, where I represents the x direction and j represents the y direction. And when I say, actually I should say, I represents the positive x direction, j represents the positive y direction. There are sometimes other representations of these. So some other things you could see, instead of I, you might, or sorry, instead of I with an arrow on top, sometimes you could see an I with a hat above, and sometimes you'll see this, an X and a Y with the hat character above them. And the meaning of the hat character means it's a unit vector. So that's just a little bit of extra meaning that can go along with that. We are going to be looking primarily at these notations. And if you were to use this hat notation, that's okay. I want you to avoid using this x hat and this y hat notation. That is used in some areas, but I'd rather we be consistent. So my preferred notation is going to be what we have here, which is the I and j vectors with the vector symbol above them. These are known as basis vectors. And what that means, a basis vector, or sorry, basis vectors, those are sets of vectors that can be used to express any other vector. So in the case of I and j, we can use I and j in combination, and we can describe any vector in R2 using a combination of I and j. So as we've looked at already, any point can be represented in terms of a position vector. And we've talked about expressing these in terms of component vectors. So some point OP, we use this notation for a vector, which is the same as the notation we would use for a point. We can now extend that to say that this scalar value A, which is the x component, and we've talked about that before as that would be equivalent to the vector A comma 0. Well, that another way to write that is to take the scalar value A and multiply it by the vector I. And so the one thing I want to emphasize here is that the value there is a scalar. The value of A is a scalar. The vector part, the direction part, is built into the vector I. Similarly, for B, that's going to be the y component. And we've represented that in the past as 0 comma b. So meaning the 0, there's no x component to this, there's only a y component to this. And of course that b value is also a scalar. So using this I and j notation, we can take any vector in R2 and we can represent it this way. Now, representing it this way is actually very convenient when it comes to algebra, because it's going to allow us to collect like terms and to group things together in a way that's very familiar to us. And you'll see that as we work through our examples. Now, before we're ready to work on some examples, I just want to take care of some basic arithmetic operations. Now, as has happened with some other lessons, we've really done a lot of this stuff already. All I'm doing right now is formalizing things a bit. So in this case, I'm going to do everything with reference to the origin O, and the origin of course occurs at 0, 0. So what I'm interested in is this purple line, which is OC. So if I had to come up with an expression for OC, How would I do that? Well, there's a couple of ways I could do it. I could follow this path going in alphabetic order. I could start with the vector OA, and then I would add this dotted red vector. But that dotted red vector is actually just the same as this solid red vector, which is OD. If we represented this using vector components in the bracket notation, the vector OA would be A comma B, and the vector OD would be C comma D. But if I want to make use of this new notation using our basis vectors, using the ij vectors, then this A is the x component, so that's going to be A multiplied by the I vector plus B multiplied by the j vector. And I'll put brackets. I don't actually need them in this case, but I'm going to put them here just to show that I'm isolating things. It's important to note that the brackets I'm putting here, these are algebraic brackets, whereas the brackets I had here, these are the brackets to denote that this is a vector representation. And for the second one, I'm going to have C in the I direction plus D in the j direction. So from there, as I mentioned, I didn't actually need the brackets, so it would have been perfectly acceptable to go to here. Now, as you're writing out all of these I's and J's, it's actually quite easy to make little mistakes. Here's a communication mistake where I've got that vector symbol. That arrow really has to go with just the J. And now I can gather like terms together. And again, I'm going to do this in an extra step or two. So I'm going to take my I values. So that's an AI plus CI plus B times the J vector plus D times the J vector. And algebraically, we can think of these I and J vectors as common factors. So I actually end up with A plus C, and the common factor is I. Normally we take common factors out front, but because this is the direction vector, it's actually preferable to leave it on the end like this. What we're saying here is I have the sum of A plus C times I, and then for this one I have the sum of B plus D times the J vector. And going back to our bracket notation, which wouldn't necessarily be something we have to do, but in this case we have A plus C in the x component position and B plus D in the y component position. Now really, I think that most of what I did here, a lot of you would probably look at this and say, well, that was quite intuitive. That's what I would have done anyway. But we need to formalize this. We need to make sure that we're following the rules that go along with this. The next thing we're going to look at is the idea of multiplication. So if I start off with a point P and then I extend along that same straight line to some point Q, how do I represent that? Well, what I've done is I've said that the point Q, or not the point Q, but the vector OQ, I'm essentially talking about stretching the vector P. So I'm going to say that's M multiplied by the vector OP. And that could be a stretch, or it could be actually a compression. So this is essentially some sort of scale factor. And that scale factor could give us a stretch. It could give us a compression. And don't forget, a negative value could also give us a reflection. So we have a reflection if the m value is less than 0. So all of these things are important to keep in mind when we're trying to figure out what this picture is going to look like. So my vector OQ is equal to m multiplied by the vector OP. But the vector OP is A comma B, but another way that I could write that is A times your I vector plus B times your J vector. Now please keep in mind, you could have done this, you could just go ahead and multiply this in. You just have to be careful. Again, this bracket, here we have a vector bracket, and here we have an algebraic bracket. And even though the results are the same, mentally it's important to recognize the difference, because when you multiply this m into this bracket, it's not the same operation as we're going to do right now. Where here we're going to use the distributive property. So I multiply this m times the first term, so I end up with ma times the I vector plus mb times the j vector. And so I end up with ma comma mb when I return to a bracket notation. Now also please keep in mind, that's fine and that is fine. Both of these are correct final answers. You're going to find that we're going to be working increasingly with this ij representation, but that shouldn't discourage you from using whichever representation you find convenient for the time. Just remember the warning I've been putting in since we introduced this notation. The downside to the bracket notation is you do run the risk of confusing points and vectors, whereas with this ij notation, there's no ambiguity there. It's very clear we're talking about a vector the whole time. And for that reason alone, I would say that this one has the advantage from a communication point of view, from a clarity point of view. Okay, so now we're going to take a look at subtraction, or a difference of vectors. And I've just put together some illustrations that I'm going to walk through here, just to I wanted to make sure, rather than me sketching things out or drawing things out. So if I start with, I've got the vectors OA and OD, and let's say I want to construct OA minus OD. So how would I do that? Well, here's my vector OD, so the reflection of that is going to be negative OD. So here we have that. I've drawn that in, or I've put that in software using a dotted line to represent the negative vector. And that means my OA minus OD is actually the same thing as OA plus negative OD. So now what I need to do is I need to take this vector and go tip to tail. So I'm going to join it to the tip of OA. And I end up with that. Now that I've done that, I have from the origin to A, and then from A along the negative vector of OD. So we're going to have our resultant vector is going to be from our starting tail to the ending tip. And that ends up looking like this. So there is my vector OA minus OD. But as we've seen before, parallelograms come into play here, and you can see that this purple vector is actually the same as the vector from D to A. So OA minus OD actually describes the vector that goes from D to A. And the ordering of that is important. So OA to OD is the vector that goes from the second one to the first one. So when we do this difference, if we were to do this difference using our I and j vectors, we start off with OA, which is AB, so A comma B, minus OD, which is C comma D. I can then break this up into an algebraic notation using I and j vectors. And then when I do that, some distributive property here, so I have minus Ci and minus dj. Bring and group those together. The A and the negative C get grouped. the b and the negative d get grouped, and we end up with a minus c and b minus d. But it turns out that that is this vector OA minus OD from D to A. And notice I try to emphasize this here. We go from the second to the first. From the second to the first. That's what we're describing. We're describing the vector. So OA minus OD is actually the vector from D to A. And you can see that as my resultant. So for your notes, I've given you a much more condensed version of that, which is that the vector the vector AB in this case. So if I'm trying to go from A to B, then the way that I do that, the vector subtraction that I do that, is I actually do OB minus OA. And so if I go ahead and actually fill some of that in, OB is equal to x2 y2 minus OA is x1 y1. Here's another reason why I don't like that x hat and y hat notation, especially for people who are new to vectors, because when we're dealing with the abstract version of these, quite often we'll be working in terms of these generic x and y coordinates. Whereas I and j, there's a convention in mathematics and physics where I and j are used sparingly for other things. So this is the same as x2 times I plus y2 times the j vector minus bracket x1 times I plus y1 times j. And this can still, you can easily make a mistake here. So now I end up with x2 times I plus y2 times j minus x1 times I minus y1 times j. And then when I factor things, I end up with x2 minus x1 times the I vector plus y2 minus y1 times the j vector. And that's perfectly fine if you were to leave that in that form, or we could write that in our bracket notation. That's x2 minus x1 comma y2 minus y1. And what that means is this represents the x coordinate of the final location, but we want a vector representation of that. So it's kind of awkward because this vector is actually the same as, there's an equivalent vector from here, because we know that the position of vectors doesn't actually matter. All that matters is the vectors themselves. But you have to be careful as to the meaning of these numbers. Remember, the numbers themselves tell you about the vector, but where you place the vector, where the vector starts and where the vector ends, that's what's actually important. Now, once we've done something like this, it turns out that the distance or the length of this line is just the distance formula that we've looked at before. So for example, between the points A and B, we would do x2 minus x1 all squared and y2 minus y1 all squared, and then take the square root. But it turns out the values that we get for the vector itself also describe that, because the values for the vectors were also x2 minus x1 and y2 minus y1 for this purple vector. So that's actually a convenient result. Okay, so let's do a few just simple exercises here. We'll start off with drawing the vector 6i minus 7j. So we're going to count out, might be easier if I actually just count out 1, 2, 3, 4, 5, 6, and negative 7. 1, 2, 3, 4, 5, 6, 7. And then we recognize that, let's see, 6i means a vector that goes from there to there. And then 7j or negative 7j is going down here. I hope you can forgive me. I know that I have arrows on both ends of these, but let me just highlight them and try to make the arrow that I'm really interested in show up. Okay, so there, and so that means my resultant vector is from here to here. And so that is the vector A. Here we had 6 times the I vector. Here we had negative 7 times the j vector. Without drawing out the I and j vectors this time, I'm going to just go negative 3 in the I direction, which would be to the left, positive 5, 1, 2, 3, 4, 5 in the j direction. And so those two converge here. And so that's the point that this vector will run to. And so I end up with that as my b vector. And then my c vector is actually a combination of these. And so drawing these actually might be quite inconvenient, but I'm not proposing that we draw it to start. We're actually going to use algebra. So the a vector is, I'm going to do a substitution. The a vector is 6i minus 7j minus 2 times the b vector, which is negative 3i. I'm going to run out of room here. Let me shift this over. Negative 3i plus 5j. And then I'm going to expand those brackets. Well, this one just stays 6i minus 7j. But here I've got the negative 2 that I have to distribute in here, so that becomes positive 6i. And then negative 2 times positive 5 is minus 10j. And so I end up with 6i minus 7j, which is negative j, or sorry, let's go back here. What am I doing? I have to combine my I vectors. So I've got 6i plus 6i is 12i. And I've got negative 7j minus 10j is minus 17j. And so as it turns out, this will not fit on the scale that I have here right now. And we can see that if this is my b vector, then minus 2b is actually taking me 2 of these down in this direction. So it would be taking me off down in that direction. And you can see, well, where is that going to end up? 12i is going to be around here somewhere. Negative 17j is going to be down here. And then those are going to meet at the destination. So given the points L 4, 2 and M negative 2, 3, find the vector that connects L and M and find the distance of L and M, and then create a unit vector in the direction of LM. So the first thing we need to remember is that LM is equal to, and if you remember when we did our subtraction, when we did OA minus OD, for example, I mentioned that that was going from D to A. You need to remember that relationship. And in that case, to reverse this, we know that to go from LM, we actually need to do OM minus OL. And the vector OM is going to be from here, negative 2i plus 3j minus bracket, and then OM is going to be 4i minus 2j. And now I'm going to do my algebra. So I end up with negative 2i minus 4i is negative 6i. And then positive 3j, this minus and minus becomes plus 2j. So that becomes plus 5j, which is, I could represent this as negative 6, positive 5. So that's my vector Lm. The magnitude of Lm is equal to the square root of -6 all squared plus 5 all squared, which is equal to 36 plus 25 square rooted, which is equal to, in this case, we have 61 square rooted. And of course, this is a positive because it's a distance. So that was for part A. For part B, to come up with a unit vector in this direction, there's a couple of things we could do, but remember the definition of a unit vector. And in this case, I'm just going to call this, I'll call this vector u. It's equal to the vector Lm over the magnitude of Lm. So I could write this a couple of different ways. I could write this as 1 over the square root of 61 times -6 comma 5. I could take this 1 over square root of 61 into the vector notation, and then I end up with -6 over root 61 comma 5 over root 61. That's probably a better representation. I could have also done this as 1 over root 61 times the -6i plus 5j. And as I did before, I would probably write that as -6i over square root of 61 plus 5j over the square root of 61. And in both of these cases, I really should be considering rationalizing. So how about I just rationalize this second one? So that becomes, in the rationalized form, that becomes -6 root 61i. And I actually have a common denominator here. If you chose to write it that way, that would be up to you. Since it's vector components, I don't know that that's necessarily a great idea. They'd be equivalent. 5 root 61j over 61. No really good or clean way to write this. So here, I've actually rationalized, which you should be doing. You are expected to rationalize your values. So these are correct answers, but here is a correct answer properly rationalized. And that's the unit vector. The length of this vector is equal to 1, but it lies in the same direction as the vector Lm. And I think this is our final example. So given the vector A in terms of I and j, and the vector B in terms of I and j, find the magnitude of A minus 2b. Well, in order to do that, what I'm really just going to start with is the algebraic expression A minus 2b. I will do my substitution, I minus 5j minus 2 times 4i minus 10j. And before I get too much into this, I should just point out the note that I've got here in this smaller text. Sometimes using vectors and vector components and being able to use the distance formula can be much easier than solving this using geometric vectors or the cosine law. So you could do this. You could lay these out. You could do a diagram. You could find endpoints. You could find angles, and you could use the cosine law to find this distance. But I think you're going to see here how much easier it can be. I've created this situation to specifically illustrate this point. So this first one, I don't have to do anything with it because the number in front is just 1. So that just becomes I minus 5j. I have to expand out this -2, so that becomes minus 8i. And -2 times -10 gives me plus 20j. I'm going to group these together, so I minus 8j is -7i. And -5 plus 20j is plus 15j. you do want to be very careful with your i's and j's here, not just distinguishing between the i's and j's, but also even how you write them. In particular, I written like this can cause problems. I really recommend, so that can often lead to a communication problem. I use a little scripted I, which you'll see this is the kind of I that comes out of a word processor if you're using an italic font, and this is what I've just gotten used to from textbooks, etc. You could also do something like this, which is an I with a little embellishment on the bottom there, or sometimes people use kind of a cursive I, so they've got that little piece there. All of those are much clearer than just a vertical line, and these are not capital letters, these are always lowercase letters. Okay, so now I've got this, and so the magnitude of a minus 2b is equal to, it's just equal to the square root of each of these vector components squared. So negative 7 all squared plus 15 all squared. And so we end up with 49 plus 225. And when I combine those, I end up with 274. So the length of a minus 2b is equal to the square root of 274. I'm not going to go through the exercise. Nothing jumps out at me here as to whether or not there's something I can extract from that. I really should simplify this radical, but when I look at it in its current form, there's no obvious factors. I don't see 4 coming out of it. I don't see 9 necessarily coming out of it. 25 won't come out of it, so I could be wrong on the 9 there, but no, I'm not wrong on 9. And I don't know any other ones that are going to come to me off the top of my head. Okay, that's it for this lesson. Hopefully that one wasn't too long, and the next lesson we'll be looking at a similar set of operations in R3.